Assalamu alaikum. Welcome to lecture 7 of natural language processing. So I hope all of you are doing well. So we are almost a quarter into our semester. This is the 7th lecture. Uh, so today we will continue with our discussion on language modeling, the n-gram language modeling. Uh, Previously, we had discussed or introduced the idea of language modeling. And we talked about unigram, bigram, and in general, n-gram language modeling. We also talked about how to estimate the probabilities using maximum likelihood estimate. So today, we will continue with first starting with how to evaluate a language model. And then we will discuss issues with MLE, and subsequently we'll discuss various ways of getting better estimates for probabilities in language modeling. So that is basically the content for today. So at the end of today, we do have a quiz as well, starting at around 11:05. So, so that is the plan for today. So any questions? So any questions? So in the last lecture, we talked about a language model or the n-gram language model. And we basically said that if you have estimated all the probabilities, let's say if you have a unigram language model, you have estimated all the probabilities for all the words in the corpus, for all the words in the vocabulary, then we say that we have a language model developed. So once you have a language model that is developed, you can use it in various applications ranging from, for example, spell correction to word prediction. For example, when you're typing something, so let's say you're typing on SMS or WhatsApp, so there will be some prediction of the word that would be most appropriate as the next word. So that also is most likely based on language modeling. And there could be other applications as well where we are trying to find the part of speech for any particular word. And then there are many other applications. Throughout this course, you will see application and usage of language modeling. So So we talked about the maximum likelihood estimate of a bigram, let's say. So W, let's say in general, I given Wi minus 1. So this is basically given as the count of the sequence of or the bigram Wi minus 1, Wi divided by the count of the context, in this case Wi minus 1. So I am writing without the subscript. I hope you can understand. It's W underscore I then minus 1. Underscore I minus 1. So this is MLE, of course, maximum likelihood estimate. And to estimate this, you need to have a corpus, which is essentially a large body of running text from which you can estimate these numbers. So now the next question is, how do you evaluate the quality of a language model? So for most, what is typical in machine learning, we typically have what is known as a training corpus or data, and on which we learn the model, meaning that the language model or meaning the probabilities. So once you have learned the model, you would typically test it on another corpus, which is called a testing corpus. So that's the standard way. But then, of course, you need to have a measure of uh, evaluating the performance of the language model on the test set. And we will talk about that very shortly. The other approach is what is known as the extrinsic approach. Uh, so let me go to the slides. Okay. Yeah. Just give me a second. Okay, this is the slide that I wanted. So how do you know how good a particular language model is? So as you know, you can use a language model to uh, estimate the probability of a sentence or a combination of word. So obviously you can use that language model to see whether and calculate the probability of a given sentence. If that sentence is correct, then its probability should be high. If that sentence is incorrect or does not follow the rules of that particular language, then its probability should be low. So a language model should then, as such, assign higher probability to correctly uh, written text and lower probability to incorrectly written text. So which basically thus points to that you will need to apply this on text which is of course correctly written and more precisely on text that is similar to the training data, because you're learning on the training data and then you're testing on some other data. If the other data is different, then obviously you will get poor probability or lower probabilities, and you will say that your language model is not good. But the language model is as good as the data on which you train it. And if you test it on similar data, then you will be better able to gauge its accuracy. If you test it on another data, you won't be able to check its accuracy. So that is the intrinsic way of uh, evaluating language model, but there's another way which we call the extrinsic way of evaluating the language model. So the whole idea here is that you're using the language model in some application, let's say spell correction, or let's say paraphrase generation. So instead of uh, calculating the accuracy of the language model per se, you calculate the accuracy of your actual application. And by varying the different language models that you have, you find out you find out the language model which is better based on the accuracy of your application. So let's say if you have a task, as I said, let's say you have spell correction and you have two language model A and B. If A gives you higher accuracy on a spell correction task as compared to B on the same task, then you say that language model A is better. So this is the extrinsic approach. You can also call this like a wrapper approach. You have some technique and you uh, have some task that you want to evaluate, and you change the technique and then evaluate the task. You change the technique, evaluate the task, and you use that technique that give you the best performance on that particular task. All right, so this is known as the extrinsic approach to, but we had alluded to the intrinsic. Extrinsic oftentimes is difficult and also time consuming. Why is it time consuming? Because we have to run the task for each language model and then evaluate the language model. Maybe you are using the language model for some other task as well, not just for that task. So you would like your language model to be good in general, not just for that particular task, but for all possible tasks that you might want to use in the future. So the solution for that is we do an intrinsic evaluation. And intrinsic, as I said, is based on a training data, which of course is always required to learn the language model. But then you also have a test data, which is similar in a probabilistic sense to the training data, and you evaluate it on that. So how do you evaluate it on that? The idea is very simple. So basically, what does a language model give you? It will give you the probability of a sentence, right? And let's say this sentence is from a test set. So, and let's say you have two language model A and language model B. So if I use language model A and I get a probability for the test set A of the sentence, and then I also get a probability of B of the same sentence. So based on these two probabilities, which basically, of course, are estimates, we will say that A is better than B if probability of A of that sentence is higher than that of probability of B, right? And we are assuming, of course, again, that this sentence is from the same distribution as the training data, and it is representing correct language. So probabilities, of course, as you know, language modeling, when you break it down, if you have a sentence and if you use a unigram model, you basically have various probabilities of 1, probability of 2, and so on. So if you multiply multiple probability, you get a very small number. So we use another measure which is directly related to probability to compare language models intrinsically. So this measure is called perplexity. So perplexity essentially is perplexity of a sentence. So this is, let me write two P's here just to indicate that this is perplexity. So PP of a sentence is basically the probability estimate of the sentence raised to power of minus 1 divided by n, where n is the number of words in the sentence. So raised to power of minus 1 over n. So 1 over n, of course, is taking the nth root. Minus means that it is the inverse. So you can, in fact, write this again as basically 1 divided by p of sentence raised to power of 1 divided by n. So it is the inverse of the probability. So, and of course, you are normalizing it, taking the nth root, which is normalizing with the number of words in the sentence. If you have a longer sentence, then n, of course, would be larger. So this essentially is perplexity. So just to take a quick example, let's say you have let's say all words are, let's say I'm talking about a unigram language model. So, and you have 4 words, W1, W2, W3, and W4, right? And we say that probability of each W1 and W2, W3 is uniform, which would mean that it's 1/4, right? Okay, 1/4. Yeah, you can say that. I mean, just to take an example. So 1/4, of course, in practice, it will be some other number, just to give an example here. So what would be the perplexity of this sentence, this sequence of words? So simply, first of all, you will have to compute. So probability of W1, probability of W2, probability of W3, probability of W4, which basically is what? 1/4 raised to power of 4, right? But then you have to take the inverse of that, right? If you take the inverse of 1/4 raised to power of 4, and then you have to take the fourth root of that. So if you do all of that, you'll get the value 4. So now this is a number, integer number, which is more meaningful or manageable as compared to points that you will get if you just computed the probabilities. So 1/4 into 1/4 into 1/4, you take the nth root and take the inverse, you will get 4. So perplexity is the inverse of probability, right? Of course, it's also normalized. So which perplexity would be considered better, higher or lower? So it is the inverse of probability. If the probability is higher, we generally consider that the language model is better fitting the test set, which of course is similar to the training set, and which then implies that its perplexity should be lower. So lower perplexities are considered better. And that's also why you call it perplexity. Higher means that the complexity or the variability of the model increases. Okay. Any questions?
Sir, in the example that you discussed, the value of n would be 4, right?
The value of n would be the number of words in the sentence that you are evaluating.
Okay, sir.
So if you are evaluating a complete passage, let's say it has 1,000 words, then you will compute the probability for the complete passage and then take the under root of it and of course the inverse of it.
And sir, we are using the extrinsic model and intrinsic model to actually compute the accuracy of this thing, right?
If you are using an extrinsic approach, you will use whatever evaluation measure is appropriate for that particular task. So let's say if your task is classification, then maybe accuracy would be appropriate.
So, sir, my point is that the extrinsic thing varies from case to case, but for
Yes.
intrinsic, you are only computing perplexity. सो मतलब दैट डजंट मतलब अगर हमारे पास केस अलग है तो हम एक्सट्रिंसिक का जो इवेल्युएशन मेजर है वो हम डिफरेंट कर लेते हैं, लेकिन जब इंट्रिंसिक की बात होती है तो हम हमेशा परप्लेक्सिटी पे ही रहते हैं, तो मतलब थोड़ा और नहीं है।
जी जी, तो द जेनेरिक वे इज टू यूज परप्लेक्सिटी विच इज नॉट डिपेंडेंट ऑन एनी टास्क, बट आपने एक स्पेसिफिक टास्क के लिए लैंग्वेज मॉडल इवेलुएट करना है तो फिर वो बेहतर अप्रोच है, एक्सटेंसिव अप्रोच, दैट इज बेटर. But if you want to
ओके सर।
evaluate your language model in general for multiple applications, and you don't want to spend too much time on using the extrinsic approach for all of those applications, then you can use and go ahead and use Perplexity.
ऑलराइट।
So इसमें the intuition here is, so the idea is like, if you have learned the correct language, so I am, this sequence of word I am, or let me increase, living in, let's say, Lahore. So the language would correctly be able to predict the next word. So let's say, let's say, let me delete this. So let's say you have reached this point, I am living. So you will have various probabilities for the next word here. Okay. So you will have probabilities for, let's say, various words, probability for Lahore, probability for, of course, given the context. Unigram में भी आप कर सकते हैं, but Unigram in general is not a very good language model. We typically be using a language model which is bigram or higher. So, but just to give an example, I'm just saying that you have multiple probabilities for the next word. So let me just write that also. Given living, right? So this is one option. Then maybe let's say living, giving, living, this might be another option. Probability of, sorry, and given, living. So you will have various options. If your language model is good, then it will assign a higher probability to in given living as compared to some of the incorrect options for a word after living. And if your language model is poor, then this distinction or this higher probability may not be correct. So that is the idea behind using language, using perplexity or probability on a test set to evaluate the performance of a language model intrinsically. So your language model will give you all of these options. A good language model would give you a higher probability for in as compared to others, while a poor probability language model might give some other word as a higher probable word. And the probability of in would be lesser. So if you compute the probability of the sentence, then you get a lower probability for the complete sentence. So which is showing that the language model is poor. So this is computing the perplexity on a real world data set. So for unigram model, you get a perplexity of 962. For bigram, you get 170. For trigram, you get 1/9. So in other words, a trigram model is a better language model as compared to a bigram model, and that is better than a unigram model if you have tested it on a real world data set with the test set looking similar to the training set. Okay. All right. So now let's move on to the whole issue of estimation. So, for example, if you consider uh, the Shakespearean writings, so we had over 800,000 tokens in the corpus and close to 30,000 vocabulary size, right? So, so there are 30,000 unique words that Shakespeare used in his writing. And of course, the total number of words that he used in his writing is over 800,000. So 30,000 vocabulary, which is distinct words, and 800,000 is the number of tokens. But if you look at his writing again, only 300,000 bigrams, unique bigrams are used by him. But if you look at the 30,000 number, the number of possible unique bigrams is much higher. So the total number of possible bigrams is 2 raised to power of 30,000, which is going to be a huge number. So the possible number of bigrams, which is the power set of the vocabulary, is tremendously higher as compared to what he actually used. So which means that if you look at his corpus, the vast majority of bigrams would not exist, would have a count of 0. So 99.96% of the bigrams would have an entry of 0 in a bigram table of counts, right? And if you recall our approach for MLE, we had the count of the bigram in the numerator and divided with the count of the unigram. So we will have many, many bigrams probabilities as being 0. And similarly, if you take any other corpus like the Wall Street Journal, it would have its own set of words, and those set of words would, of course, those set of words would have a different set of vocabulary, and this vocabulary may not entirely overlap, would not be exactly the same as that for any other data set. So let's say you have trained a language model on the Shakespeare data set, and then you tried to apply it on the Wall Street data set, even if, let's say, you had used a good estimation approach, you will get very poor results. But let's say if you have used the MLE approach, as you can see, there are tons of pairs of words that Shakespeare did not use. But maybe those pairs of words were present in the Wall Street Journal corpus, and that would give you an error, or that would give you an incorrect uh, answer because it was not seen in the training set, which is a Shakespeare, and you tested it on the Wall Street Journal data set, which is the test set. So the issue of zeros is quite profound in natural language. As I said, vocabulary is large. The number of possible bigrams, and we are talking about bigrams. If you go to trigram, it will be even larger. So number of possible bigrams is massive, but the actual number of bigrams that is often used in practice and that is, of course, dictated by the rules of the language, is very small. So this whole idea of zeros and testing on a different data set is in general called overfitting in the machine learning domain. So you're learning on a training set, and you would like that learned model to work well on other test sets also, not just exactly the same training set. So that is robustness or generalization. So in real life, this is not always the case. For example, you learn a language model on a huge corpus, let's say, but still you will be applying it on some other data set, which might be somewhat different. And you would like it to apply to different data sets, not just one data set. So robustness or generalization is very important in language models. And one of the issues that we have seen that we would like to handle is the issue of zeros. Zeros essentially meaning that there are so many possible bigrams in this case that do not actually occur in the corpus, the meaning that its count is 0. So that might occur also in the test set. If it occurs in the test set, you will get an error of 0, or you will get a probability of 0. So this is just a simple example here. Let's say you have a training set. So you have several similar phrases: denied the allegation, so let's say you have various options in the training set, but in the test set, there is the denied the offer, denied. So all of these are denied the report, denied the claim, denied the request. This is the training set. But in the test set, you have denied the offer. If you learn on the training set, you will not find that sequence denied the offer. And when you go to the test set, it will assign a probability of 0 to that, even though it is correct sequence of words. All right. So if you compute probability of a bigram in a test set, which is 0, and you use that to estimate the probability of the probability of the test sentence, you will get a value of 0. And let's say if you're using perplexity is dividing with 0. If you cannot divide with 0, you get a overflow error. So this, and of course, this is incorrect because, and since we said there's so many zeros, so your test set will always give you a probability of 0, which is incorrect. So the remaining of this chapter is basically discussing some ways of alleviating these issues in the estimation of the probabilities. Okay. So let's look at various approaches to get better estimates. So one simple approach which comes from, and most of these approaches can be called smoothing. So smoothing approaches for getting better estimates and to avoid the issue of zeros in our estimates. So we will start with some basic ones and we'll also see the issues. The first one is basically the simple add one smoothing, which is also known as the Laplace smoothing. Laplace because based on the Laplacian prior that is applied. If you look into the machine learning theory of this, then it means that you're assuming a prior distribution of that particular event. In this case, of course, a word or bigram. But we won't go into that mathematical detail. We will just show you the formula. So what is the add one smoothing formula? So basically what we do is we assume that for each word, we are adding one more word. So if a word does not occur 0 times, so we'll have at least one of that. So, and of course, we are talking, when I say word, it means in general, whatever the unit of bigram, n-gram that you're interested in. If it is bigram, then it's bigram. If it's trigram, then it's trigram. So let's say we are talking about bigrams. So let's say the formula for computing the I given I minus 1 using plus 1. So this bigram or every bigram is assumed to have one more observed example, and then divided by the count of W I minus 1 plus. So we have added one word, one bigram. Uh, so, and if you add the entire row for each word, essentially uh, you're adding the for each. So you're adding V, which is the total number of vocabulary, more words into the corpus. So basically, so let me explain this. Let me write it down first and I'll explain later. V. So you're adding the vocabulary into the denominator. So for example, we talked about the 2D bigram matrix. Let's say you have the word I am. So this is, let's say, the bigram C. Let's say its original count was, let's say, 300. All right. So what we are saying is that so I is a row, M is the column, right? In the 2D matrix where you put this 300 value. So for each word, for this each of this bigram, for each I, with every other word in the vocabulary, you add one. So how many more I's have you added? The total number of vocabularies. And you can flip it the same way. So I is the preceding word, M is the other word. So how many, if you want to count the number of times that M has been added, so if you sum all of them, you have added one more M, because in each row you have added one more of that. So how many, what is the size of the number of columns and number of rows, which is equal to the vocabulary size, number of distinct words in the data set. So this is basically add one smoothing. So you are assuming that you adding one more of that particular event, in this case bigram. So you'll add one in the numerator. In the denominator, if you count the number of times that has been increased, it will be equal to V, which is the total number of distinct words in your data set. So this M1 Laplace smoothing or add one smoothing can be used to remove the issue of zeros. But for NLP, it has some issues we'll discuss shortly. Although this is somewhat quite popular and also usable for many other machine learning applications. For example, for classification tasks, even for text classification, this works well. But for language modeling, it doesn't work well. So we'll see why it doesn't work well. So let's so this is the formula for the advanced estimate. And of course, this is different from the maximum likelihood estimate. So this is the Berkeley restaurant corpus, and this table is showing you the bigrams. And this is the bigram counts after Laplace smoothing, meaning that you have added 1 to each number. If you compare this, if you compare these bigrams with the previous bigrams that were in the previous slide, you will see that for each bigram, 1 has been added. Okay. So this is the Berkeley restaurant corpus bigram raw count table. So here we have the Laplace smoothed probabilities. And you will notice that there are no zeros here now, because all the zeros have been converted to at least one observation, and you will get a probability which of course might be very small, but not zero. So the issue arises is if you reconstitute the counts, and based on that, you would notice that you have taken a lot of probability mass from the events or the bigram that actually occurred to give to those that did not occur. That changed the distribution drastically. So, so just to uh, what is this? Okay. So remember the Shakespearean corpus. So 99.96% of bigrams were zero, right? Meaning they did not occur in the corpus. And if you create the 2D table, you will have all combinations. ऊपर भी आपके पास 30,000 words होंगे, row में भी 30,000 word होंगे, and some combination of those words and many combination of those words would have a count of 0. तो Laplace smoothing में effectively हो क्या रहा होता है? You are actually moving probability mass from those bigrams that occur to those that do not occur or have a count of 0. But the vast majority of bigrams have a count of 0. So it means that, so let me just take a simple example. Let's say 10 bigrams had a count of non-zero, and let's say 10,000 had a count of 0. So what would happen is you are giving 1 to those 10,000. So you are removing 10,000 counts from those 10 observed bigrams so that you can give 1 to those that are unobserved. So what happens is those 10 जिनके observed counts है वो drastically change हो जाते हैं. Do you get this point? So let's say 10 में let's say एक कोई count था, let's say 300 था. So 300 कोई और count था, let's say 20 था, कोई और count था 500 था. So हर एक में से आपने इन सारों में से यही आपके पास pool है जिसमें से आपने सारों को 1 दिया. You have to give 10,000 away. So 10,000 away का मतलब ये है कि मे बी कुछ जीरो हो जाएगा यहाँ से, या बहुत जीरो तो खैर हम नहीं करेंगे, 1 कर देंगे इसको, कोई बहुत थोड़ा हो जाएगा, 2 हो जाएगा, कोई 5 हो जाएगा. So those numbers have been drastically changed. So in other words, you are changing the distribution significantly and changing what is actually occurring in the data set by this smoothing technique. So this smoothing technique only works if it is the flip side, meaning that you have 10,000 events or bigrams in this case that are non-zero, and let's say only 10 that are zero. And then you're moving the probability mass from those 10,000 to only those 10, giving 1 to those 10. So you're only reducing those 10,000 counts by just 10. While in the previous case, you're removing the count of 10 words, reducing the count of those 10 words by 10,000. So those counts would change drastically. So which is not desirable and would give erroneous results. So you can also understand this by computing the reconstituted counts. So reconstituted counts means that the counts after you have added uh, the one, so the new counts would be significantly smaller. So, so how can you do that? Let's say you say the new count is C star of any, let's say, bigram Wi minus 1 Wi. So this would be given by previously you had the probability that you computed was C Wi minus 1 Wi plus 1 and divided by, of course, what was in the denominator C Wi minus 1 plus V. And this whole thing you multiply with the prior Wi minus 1. So this will give you the reconstituted count of uh, this particular bigram, because you are now using the probability uh, based on the add one smoothing and multiplying, which is of course prior, you will get the new counts. And if you look at these new counts for the Berkeley, so you notice you here in this figure, you see the raw bigram counts as well as the original the reconstituted bigram counts. So the lower image, lower table is for the reconstituted count after applying Laplace smoothing, and the upper one is the one with the original raw count that you actually observed. So you'll notice that for some words, or for most of the words, the counts have changed drastically. Why have they changed drastically? Because we have moved those counts to those bigrams that did not occur. Of course, this table is just a subset of the whole Berkeley corpus. So of course, we can't show all those 10,000s of columns and 10,000s of rows in this small table here. But in this table, there will be many zeros elsewhere. So all of them are not shown here. But the idea that we are trying to highlight is there are many zeros that have taken away probability mass from those that are non-zero, and those non-zeros have changed drastically as a consequence because those zeros were in very large numbers. So any question here? Is this point clear? So advanced smoothing is a popular technique for many machine learning um, estimates, uh, for naive Bayes, for logistic regression, and other probabilistic models in machine learning. But for language modeling, as we have shown here, because of the because of the numbers that are actually zero and the number that are actually not zeros, it is not a good approach for smoothing or getting better estimates. So this is, as is mentioned here, is a blunt instrument. It's kind of like a sledgehammer that takes all the counts away from those few words or bigrams that have a count to those that do not have a count. Okay? So now let's look at some other approaches. So let's look at some other approaches. All right. So the first one is basically what is called back off. So essentially, backup means that let's say you're trying to find the trigram probability, something like probability of Wi given Wi minus 2, Wi minus 1. So if this probability, or let's say if this count is not, so for this, what you need the count of Wi minus 2, Wi minus 1, and Wi. So if this count is 0, or let's say very small, 1, 2 maybe, so it will give erroneous results. And as you go to longer length n-grams, you will find in your corpus that they are found to be 0. They are not present in the corpus. So if this is the case, you basically estimate this with lower order n-grams. So we wanted to estimate probability of Wi given Wi minus 2 and Wi minus 1. You approximate it with the lower order, probability of Wi given simply Wi minus 1. So you have dropped one context. So back off to the previous. Okay? Or even if this is too small, you can even go back off to the unigram. So maybe you can simply back off to simply probability of Wi. So whenever you find that a count is very small, you can simply back off to the previous order n-gram estimate for that probability. So this is one very simple way of making sure that you have fewer zeros in your language model. You can extend this idea further through interpolation. So for example, let's say you want to find the probability of the bigram Wi given Wi minus 1. What you can do is, so of course, this is Wc Wi minus 1 Wi divided by C Wi minus 1 plus some parameter, let's say lambda, non-negative parameter lambda, into probability of Wi, the unigram. So this is the interpolation way of it. Not just simply back off. Back off would mean that just use probability of Wi. Here we are saying that we add that number there as well. Maybe that is 0, maybe that's very small, but with that we add a parameter lambda with the unigram and use this for the estimates for the bigram. And you can do this, continue this for trigrams and higher order n-grams as well. And of course, so this PWI, of course, as you know, can be estimated simply by C of Wi divided by N. N, of course, is the total number of words in the corpus. Now, obviously, the question is, what is lambda? How do you find out lambda? So lambda is a parameter. So lambda in general should be greater than or maybe even sometimes equal to 0, although equal to 0 means that there is no interpolation, but it cannot be negative. Okay. So how do you find this lambda? Again, you use the machine learning approach of a training set and a validation set. So you train your model with some learn with different lambdas on training set, then basically evaluate on validation or test set, validation. So when I say evaluate, basically we're evaluating the language model. So language model evaluation, if it's intrinsic, it is perplexity. So you will then find for which lambda uh, the perplexity is minimum on the validation set. So you'll keep that as the selected parameter for lambda, selected value for lambda. ठीक है? So we talked about backoff, which is simply going back to the previous order n-gram if a higher order n-gram count is unreliable or zero. The other approach is to use an interpolated estimate for the higher order n-gram plus some parameter into estimates for the lower order n-grams. Okay, and that parameter can be estimated in a validation data set by selecting various values of lambda and finding the one that gives you the best performance on the validation set. And of course, the approach that I talked about is simply linear interpolation. And that is, of course, the one that is used in practice. Non-linear is kind of impractical. So how to set the lambdas? We have already discussed this. You need a training set, you need a validation set. Learn the model of the training and evaluate on the test set or validation set. Choose the lambda that gives you the best performance on the validation set. Another issue that arises, and that is a cause for the zeros issue, is the issue of unknown words. So what is the unknown word? Sometimes it's also called the OOV problem, out of vocabulary problem. So what does that mean? Meaning that you have a training set, and from the training set, you have developed a vocabulary. Vocabulary, as you know, is a set of unique words or distinct words or types in your corpus. And you have trained your model on the training set. But when you go to the test set, you maybe find out that there is some word that was not present in the training set. So that word would then become a out of vocabulary word. It is not seen by your model. So in other words, let's say, all right. So let's say there is some weird word, let's say like unfriend, for example. So unfriend did not occur in the training set, but it occurred in the test set. So if it occurred in a test set, you won't have the probability of unfriend available to you. So you do not have this probability. If you do not have this probability, what should you do? Do you assign a value of 0 to it? If you assign a value of 0 to it, then of course the whole computation of the probability would turn to 0 because there was one word that was OOV. Okay? So to handle this, there's a very simple approach which is commonly used, is to define an unknown token or vocabulary, UNK, UNK, or whatever you want to give it. Let me put it in braces. So this is UNK is a new type or vocab item. So what do we do? In the training set, you select some words that are very rare in the training set. So let's say in the training set, there are some words that are very rare. Uh, let's say Chicha, Watni, for example. This is I think, a place in Punjab. Actually, there are two characters, but let me just say So let's say this word did not occur in your training or occurs in your training set, but it is very rare. Maybe it occurs just once. So you do not keep this word. You replace this word with the UNK token. And you do this for others as well. Let's say ये जो वटनी है इसको भी आप UNK कर दें. And maybe some other less frequent words, let's say कोई और ले लेते हैं, let's say lambast, इसको भी आपने UNK कर दिया. अब आपके ट्रेनिंग सेट में ये वर्ड्स नहीं है, लंबास नहीं है, चीचा भी नहीं है, वटनी भी नहीं है. They are all replaced by UNK. So you will now compute the probability using UNK. So you will have this probability now estimated. All right, so we have 4 minutes left. So this probability is estimated. So whenever this probability is estimated from the training set, and whenever you find a new word in the test set, let's say in the new word you found some other weird word, let's say unfriend, for example, again. So for unfriend, you estimate the probability of unfriend you approximate it with probability of UNK, okay, which you already have from the training set. So this is one way of handling out of vocabulary words in the test set, out of vocabulary words that appear in your application. So I think I'll stop here. You have a quiz in a couple of minutes. So any questions? Any questions? So get ready for the quiz then. The quiz starts in a couple of minutes. And of course, you do have some select time as well. So anyone has a question, he or she can ask. So please have your cameras on as well. And in general, even though we do ask you to for compliance, but I'm assuming that all of you should follow good ethical practices. Don't do any cheating. It's good for you in general. So getting, let's say, 2 more marks in a quiz won't help you in the long run.